Face recognition. We want to match faces in images to one of the known subjects in our database. I am using 11 classes of the publicly available dataset called CASIA Web Face that includes more than 10,000 identities in it. Then I divide my dataset into train, validation, and test. In test set, I only keep one image per subjects only for visualization purposes, and the remaining pictures are in train and validation. For setting up my environment, I create an environment with Python Anaconda 3.76 and then install the required packages. One of the required packages in this project is the Keras VGG Face package available in GitHub. The remaining required packages are listed in the submitted requirements.txt file. In this project, first I use two pre-trained models with VGG16 and ResNet50 architectures. Then I try to improve these models using feature extraction, transfer learning, and fine-tuning. In this step, I'm creating 8 new models and I compare their training and validation accuracy and loss. Then I want to explore what happens if we want to add another person to our database. And what if we want to classify an image that does not belong to someone in our database? Or what if in our database we only have one image per person? In this step, I use embedding extraction and comparison of embeddings on a pre-trained model called FaceNet developed by Google. In each model development, I try to test the models on images that have multiple faces in them. Before going through the first step, we need to identify the part of the image that is the face and extract that. For that, I'm using a package called MTCNN. If there are more than one face in an image, then I get the face that has the larger area. Then I test the VGG16 and ResNet50 models that are pre-trained on VGG Phase 2 dataset. This dataset includes more than 9,000 celebrities in it, and it also contains the 11 celebrities in my dataset. VGG16 identifies 3 out of 11 faces in my candidate samples, and ResNet50 identifies none of them. Then we extract features and labels of the train, validation, and test images by predicting from the convolutional base of VGG16 and ResNet50 models. Then I create a model and feed these extracted features and labels to that model. In order to avoid overfitting, I'm using dropouts and regularizers in this model. The results on top are for VGG16 architecture, and the below are for ResNet50. We see that in both cases, validation and training accuracy remain constant through 20 epochs. Next, I built a model on top of the convolutional base of the VGG16 and ResNet50 models. Then I freeze the parameters of their convolutional base and only train parameters of the added hidden dense layers and classifier layers. Again, I'm using dropouts and regularizers to avoid overfitting. In this step, I'm using a horizontal flip, 45 rotation, and zooming for image augmentation. The results in this slide show VGG16 architecture when added one hidden dense layer on top or added 2 hidden dense layers in the bottom. We see that in both cases the validation accuracy is 94%. Then in this slide we are looking at the result of ResNet50 model. We see that when added 2 hidden layers, the validation accuracy increased from 76% to 94%. The next improvement is fine-tuning. In this step, again, I'm building a model on top of the convolutional base of VGG16 and ResNet 50, and I only unfreeze the parameters of all layers in the last convolutional block, and the remaining layers in the convolutional base are frozen. Then I retrained the parameters in the last convolutional block and added dense and classifier layers. Again, regularizers are used to avoid overfitting. On the right, we see that the last convolutional layer is the parameter is trainable and the remaining is not. In the result, we see that fine-tuning improved accuracy of both VGG16 on top and ResNet 50 below. The greater improvement is for ResNet 50, from 94% to 97%. Here is an illustration of all transfer learning and fine-tuning models. We see that all the models have correctly predicted the candidate pictures except the model of ResNet 50 transfer learning that uses one dense hidden layer, which had 76% validation accuracy. How about having less clear images? Here we have an image that is not as clear. It has multiple faces and does include faces of people that are not in our database. All subjects are correctly identified using all models, but the subjects that are not in our database are predicted as one of the classes in our last classifier layer. Now we want to know, what if we want to add another person to our last classifier layer? Or we want to also be able to classify those people that are not in our database. If we want to use previous models, then we need to retrain them by including new classes in the last layer. We also want to examine what happens if we only have one image per person in our database. Then we cannot really use our previously developed models, because those use a large number of images to learn each class of the subjects. Here I'm trying to explore the FaceNet model that's developed by Google, and it's trained on the MS Celeb 1 million dataset. This model, instead of learning a map from images to classes, this model learns a mapping from images to embeddings. Therefore, we create a people's directory including one image per subject in our database, and then we find the embeddings of each of these images and store them. Then for each candidate image, we compare the embeddings of our database with the candidate image database, and we use a predefined margin to say that if the distance between two embeddings is more than that margin, then those two embeddings are not the same person, otherwise they are the same person. Here I'm using the results from the repurposed FaceNet model. The images are less clear, they have multiple faces, and they include faces that do not belong in the database. We see that all of the detections are correct. Lessons learned. Repurposing existing pre-trained models, even using a moderate-sized dataset, can significantly improve the prediction accuracy of those models. The performance of repurposed models, however, strongly depends on the underlying network architecture and not necessarily the depth or the number of layers. We saw that although ResNet 50 has a lot larger number of layers, the VGG 16 had better predictions before repurposing. Even in transfer learning, VGG 16 with one layer achieved the 94%, but ResNet 50 only achieved it when added 2 layers. Then we saw that fine-tuning improved the validation accuracy of both VGG 16 and ResNet 50 models. Then models using VGG 60's convolutional base responded better than ResNet 50 to transfer learning, regardless of adding 1 layer or 2 layer. But ResNet 50 only achieved to that accuracy when added 2 layers. On the other hand, models using ResNet 50's convolutional base responded better to fine-tuning and had a greater improvement in the validation accuracy compared to its transfer learning instance. And the last lesson is that the performance of repurposed models strongly depend on the number of images in the underlying data set of the pre-trained models and the learning algorithm of them. Repurposing FaceNet model with 1 million identities, which uses a one-shot learning algorithm, strongly overperforms unmodified version of the pre-trained VGG 16 and ResNet 50 models that all trained on 3.5 million images of about 9,000 identities. Thank you.